All right, let's get started. Uh, so last class, we talked about two very important results, ideas and results, really. One was universality. Okay. And the other was uncomputability. Okay. And for uncomputability, we saw two functions which were uncomputable, toddler and halt. Today, what we're going to do is explore this idea of uncomputability more, find more uncomputability. In fact, as it turns out, it's really everywhere. You don't have to look that hard if you know the right way to look. And that's what we're going to talk about today. In particular, we'll discuss more about reductions and something I'll call meta-programming. Okay? All right. And just a reminder, exam 2 next Wednesday, 11/19, 2 to 3:50. Same rules as before, no notes. And there will be a few multiple choice questions and few regular questions, all previous year's exams. Okay. And the main concepts, again, it's lectures 9 through 14. So pretty much regex, pumping lemma, Milnor theorem, Turing machines, like uncomputability, for example. Okay, so these are the topics that will be on the exam. So starting from lecture 9 all the way to today. Okay. And in terms of practice, I would recommend going over the material, understand the main concepts, Mementi, pumping lemma, and uncomputability. And some of these things involve some guesswork in the sense that you need to develop your intuition. Okay. So to do that, it's try problems. Okay, you're honing your intuition. So if you read a solution, it'll make sense, but then you wouldn't understand how to come up with the solution for the next problem. Okay, so for every one of these previous year's exams or the homework problems, just try them a little bit. You want to develop your intuition and guessing, for example, the challenge string, or for uncomputability, like what do I reduce from, and things like that. Okay, and so practice makes perfect. So really keep that in mind. And discussion section on this Friday will focus on exam review. Okay, the TS will have some plan, but if you have something else in mind, just go to the discussion sections and ask, and I'm sure they'll be happy to accommodate. Any questions about the exam? No? Okay. Homework 4 solutions will be posted as soon as the deadline is done on Monday, so you'll also have time to review those. All right. Okay, so let's get started with our actual content. Last class, we saw two important theorems. The first one was that toddler, which is a well-defined function, is uncomputable. Okay. And we use this to also show that halt where we define it as halt as two inputs, m and x, the description, it's always the description of the machine and an input x, and it's 1 if m halts on x and 0 otherwise. Okay. All right. And we showed that halt is also uncomputable. Okay. And it's a really, it's not just uncomputable because there are some strange inputs where you don't know the value. It really shows up as a very hard problem on things that we care about. Okay. So oftentimes, if you have a compiler or interpreter, you would really like to know if you're being asked to run a program, whether it's going to halt or not. If you could do that, you would save lots of time, lots of security issues. Imagine you're a cloud service and someone gives you a trivial while loop. You can flag it immediately instead of running the program and wasting whatever compute you have. Right? For simple things, in fact, many IDEs do allow such heuristics. They'll say, OK, you didn't increment the counter, whereas the while loop has a counter. So you're going to run into an infinite loop. But these are heuristics. They don't capture many things. Okay. And it turns out, it is actually a very challenging problem, an important problem in practice, but one that we cannot solve. Okay. All right. So we already saw one proof that halt is uncomputable. And towards the end of the last class, we started working on another proof. And as I said, it's an important enough problem that it's worth doing it twice. Where is the other proof? Oh, there we are. Okay. So here's the second proof. So to do the second proof, we said, suppose halt was computable. Right? Then I'm defining this new strange program called can'tSolveMe. And it does something seemingly weird. It takes whatever input it's getting and running halt on it. Okay. So it runs halt on the description of M, and the input is also the description of M. And if it's saying if it halts, then it's going into infinite loop. And so it's implicitly kind of doing the same, do the opposite of what you're expected to do, right? So in some sense, this is saying, if I halt, then go into an infinite loop. If M halts on M, go into an infinite loop. Otherwise, you return 0. Okay? It's just 4 lines of code, but it's 4 very clever lines of code, I would say. All right? Okay. My claim is that we arrive at a contradiction. This should not be possible. And the reason it should not be possible is because halt cannot be computed. Okay? So why is that? We're going to make the snake eat its own tail and ask, what is can'tSolveMe of can'tSolveMe? Okay, there is still something self-referential going on. You're feeding the source code of a program as input to the program, right? As I said, this is where kind of it gets a little bit counterintuitive in that you can view programs as inputs to other programs. Okay, and once you think along this line, I think many things become simpler. So you have to get around this obstacle of thinking of programs as things that manipulate stuff, but really think of them as I can even give them as input even to themselves. Okay, there's a self-referential thing going on here, but if you accept that, then everything is a bit more intuitive. Okay. All right. So what is this guy? It has to be 0 or 1, or let's see what happens, right? So what is it supposed to be? So imagine can solve me of can't solve me is 0. Okay. So, if the output is 0, then the program actually halted, right? If you're getting an output, then you should have halted, right? So this implies that if I run my halting checker on these things, right? So if I get an output of 0, then I did halt. So halt will say, okay, you're actually going to halt, but then I'm going to go into an infinite loop here. Right? So you're kind of having the same toddler behavior. You check if you're going to halt. If you're going to halt, then I'm going to run forever. Right? If you're not running forever, then I'm going to get a contradiction. Okay? So this implies that can solve me enters an infinite loop. Okay? And this is a contradiction. Right? So if I don't terminate, if I terminate, then I shouldn't terminate, which is a contradiction. And in the same way, if did not terminate, meaning let's say it went into an infinite loop, then what should happen? If it went into an infinite loop, then you would never enter here, so you would just come straight here, right? So that's the weird thing. So if you're not stopping, then you would detect that you're not going to stop. Okay, which is another contradiction. All right, so there's no way around this obstacle, right? Once you can feed yourself as input, if you start asking questions, you can easily do the opposite of what you're supposed to do, right? And that's what you're doing here. And also the same thing was implicitly happening in toddler. So here we're saying, okay, if I'm going to halt, I'm going to go into infinite loop. If I'm not going to halt, then I'm going to actually halt, right? So very contradictory. So this implies that halt itself is uncomputable. Okay. So if we get around this sort of concept of having programs as inputs, then a lot of this stuff is a little bit like, you're checking all the cases. Okay, if this, then what, and so on. Okay, but we have to internalize this notion that I can give programs as inputs, and I can also give my own source code as input to myself for a program. Okay, does it make sense? Any questions about this? All right, okay. So we have two uncomputable functions, but it turns out that actually it's not just these two, but uncomputable functions are really everywhere. And the way we can handle them is through reductions. Okay. And we are going to look at some kind of a subclass of reductions, which are called CARP reductions. Okay. I mean, the general reduction, this is a special case, but I think it kind of, these are simpler to understand and are almost as useful. Okay. So what's a reduction? Reduction is essentially, instead of solving problem A, I'm going to solve another problem and use it to solve problem A, right? So meaning, okay, so imagine I have some problem that I want to solve. Some computational problem, maybe I want to find out if some graph has some property, or some string has some property, or some image has some property, or if some program has some property, and so on. Okay, and have all kinds of inputs for this problem. And the reduction is basically a map which takes inputs for one problem to inputs to another problem. Okay, so x goes to R of x. Okay, so maybe I'm going from the space of images to numbers, right? Or maybe I'm going from strings to numbers, or numbers to strings, or text files to text files, or whatever else you have, right? So you're mapping inputs for problem A to inputs for problem B, right? So it's just a function of this form. Okay, and since all of our inputs are just binary strings, we should just think of reduction as a mapping which takes binary strings and gives out binary strings. Okay, and we desire three properties out of this. First, you need to tell me what the reduction is. So let's call it specification, or what. Basically, you have to tell me how am I computing this transformation, right? And the next one is perhaps the most important, which is utility. Okay, or the why. Okay, think of it this way, right? So someone gave you a library which can solve problem B. Okay, some magical box, something sitting in the cloud, which can solve these problems for you. And you want to solve these problems. So what do? You transform the input here into something here. Okay, and then solve problem B on it. Okay, so that means I need to be able to say, I want to compute A of x, some function, or A, which is my problem A. That should be the same as solving B on my transformed input. Okay, does it make sense? So instead of solving problem A on my original input x, I'm going to massage it and then outsource this solving to my Oracle, which can solve B. Okay, it's sitting somewhere in the cloud. I say, hey, can you solve B on R of x? And the claim is, or it is useful for us if we have this equality. Okay, and often, really when we're doing a lot of programming, except for very simple tasks, we are using reductions to various libraries or function calls, right? Okay. And then you have to tell me the implementation. On the how. I'm just breaking it down as 3 steps, but technically, for most cases, some of these will be self-evident, so we don't elaborate too much. But you should always imagine that these 3 steps need to show or make sure R is computable. Okay, so we need to make sure that the transformation itself isn't too difficult, right? If the transformation itself is too difficult, then it's not very useful for us. Okay, so we need something which is computable and maps inputs from one space to the other, and you have these properties. Okay, yeah.
Like the outputs from like problem A have to be the same kind of outputs as problem B. Like, is there no sense if like we solve problem B and I'm gonna map that output to back to A?
That's definitely possible. In fact, there's a name for that. Excellent question. So those are called Turing or Cook reductions. And let's say can make multiple calls to B, can further process. Outputs of B. But this is what you're asking, right? So you can definitely do this. This can also work just as well, but I'm simplifying the search space for us because CARP reductions are, as I said, they are quite widely useful and they're simpler to think about. Okay, so instead of imagine if you have a library call, usually we don't just make one call, right? You can make multiple calls to it, and you get a result, and then you massage it, and then maybe you make another call, and so on, right? But in this, at least for the problems that we are going to study, CARP reductions themselves are enough. Okay. Any other questions? Okay. All right. So we know kind of what reductions are now, or at least we've defined them, and let's see them in action. In some sense, we already saw a case of a use of reduction for showing halt is uncomputable. But now I'm going to define another function, which I'll call halt on 0. Okay. And it's in some sense an even simpler function than halt. It takes a description of a program as input and just tells you whether or not the program halts when the input is 0. That's it. Okay, so it's really, I just want to know if my input program halts when 0 is the input. Again, there's nothing special about 0. You're basically saying I want to know if it's going to halt on some specific value. All right? And the claim is that halt on 0 is also uncomputable. Right? Is uncomputable. It makes sense that halt on 0 is kind of easier than halt, right? If I can solve halt, I can easily do halt on 0. I just plug in 0 as my second input. But here we're saying, okay, that's obvious, but the other thing is also true, that halt on 0 is really just as challenging. It's also uncomputable. Okay? And the way we'll prove this, or kind of investigate why this is true, is by using reductions. And we only have 2 problems so far to start from, so I'm going to pick one of them. Okay? So I'm going to pick halt. Right? So I want to say that I can solve halt if I can solve halt on 0. It's a little bit counterintuitive. Okay? The other direction, as I said, is kind of more obvious. But this direction is trickier. So what are the inputs for halt? Usually I have some program. So I'm going to write as this sort of text file. And then I have some input x. Okay, so the inputs for halt are pairs like this. Source code of some program and some potential input x. And then I want to check if the program is going to halt on this input. And then I go to here. And what are the inputs for halt on 0? There's just single programs, right? There's no other input. Okay, so we want some way to take this pair and output a single program. Again, we are allowed to design our source code however which way you want, right? So the source code that I write down can depend on both of these ingredients. Okay, and what is the property that we want? The most important property is the utility part. If I call my oracle on this transformed input, I should get the answer to the original question that I want. Okay? And any ideas on how I can construct this reduction? Sessions. We are transforming one program with the input to another program. That's what we are doing. Sessions. So imagine, like let's say I tell you, as an analogy, I have this. I give you the source code of some file, the Python code and an input x, and then I want to transform it. Okay? Any ideas? Okay, so if you haven't seen it, for example, in Python, I can do this. Let me define a new program. Okay, what is this doing? I'm just calling the Python executor on m.py, x. Okay, when I say I'm calling, I'm cheating. I'm not really calling. I'm writing down the instruction to call. Okay, so I have a new program now. This is n. Okay, I've just written down the source code for this program. Okay, and in the Turing machine world, it would be something like this. I get as input m and an input x. And here's how my reduction is going to do. It's going to take these two text, first is a text file, one is a bit string, let's say, and is going to output the equivalent of the following. Okay. what it's really doing is it's hard coding the input for X. Okay. And we are not running. So the reduction is not running M on X. It's writing down the instruction which says, okay, run M on X. There's a difference between the two. It's a very important difference, right? So the reduction is only manipulating text files here. It's only manipulating the source code, and it is not doing anything too complicated. It's never executing this, right? So it's only transforming one text file to another. Okay. So it is computable, as in I'm not going to end up in some infinite loop or anything because I'm never running this. I'm just saying it's the instruction that I'm writing down. Does it make sense? Any questions? Yeah? Oh, so the dark blue one is basically Python speak, and this is Turing machine speak. Okay? Yeah, essentially they're doing the same. Okay, so here, I mean, this is a real command that you can call, not with Python, but Python 3. This is a real command I can call in a Python program. Okay, whereas in the Turing machine world, I would say, okay, you run eval. Right? So all I did was take the source code for M, the input X, and hard coded it into this executor command. That's it. I'm not executing it. I'm just saying, okay, this is my new program, which asks you to execute it. All right. Again, as I said, it's only one line, but it is confusing because we are manipulating programs. So this meta reasoning is a little bit counterintuitive. Any questions about this? Yeah? Sorry, say it again. So I'm asking eval is our evaluator, right? Okay. I'm saying, okay, write down all of the instructions. So eval, for example, there is a Turing machine for it. There's a set of instructions you can do to compute it. I'm just writing down all of those instructions with M and X as the specific inputs. So I'm hard coding the input for M in some sense. Okay. So we're not, we're just transforming source codes, right? We're not running M on X. We, as in, our job is to do the reduction, right? The cloud or the oracle in the sky is going to solve N, so we don't care about that. Our job is to just transform one program into another here. And the new program that I want my oracle to compute is this guy. Okay. And since my reduction knows both M and X, it's, I can definitely do this. Write down this new program. I'm just writing down the instructions and passing it along to my oracle in the sky. Okay. It can do some weird stuff. That's fine. I mean, that's the assumption that we are making. So I'm pushing all of the difficulty to it after I manipulate the program. Okay. So what does this imply? So let's check, right? The first thing is R is computable. This is the how part, right? And it's kind of, we don't even have to prove it. We're just writing down the instructions, right? I just added one like text file here, M is here, X is here, the return one. So all of this is doable. Okay, yeah? N is the output of R. Okay, so R takes a program as input, program and X as input, and outputs another program, right? So the entire description of N, the source code of N, is the output of R. Does that make sense? Okay. Like, for example, if you go here in Python, it would say it will take the source code X and then just copy the entire source code, let's say, and X as like one long string and X, and then that would be my N. Okay. Yeah, so R is only out, the output of R is exactly this guy. Right? So it is clearly computable. And now let's check the utility part, which is, as I said, is where stuff really happens. So what do you want to say? I want to say that to compute whether M halts on X, I can push all of the hard work to my oracle in the sky, which is purportedly solving halt on 0. Okay. And now this is like a case analysis. So you say if halt of M comma X is 1, if M halts on X, then does N halt on 0? In fact, it has the same behavior on all inputs, right? So N has its own input. It's essentially ignoring that input and running M on X, right? So if M halts on X, then halt on 0 of N, the new program that we wrote down, also equals 1. Okay, so when I plug in 0 here, I'm still going to halt and return 1. And in the same way, if we had the opposite scenario, M does not halt on X, okay, then this would go to a loop on every input, in particular even on 0. Right? So this implies halt on 0 of N equals 0. Okay, so we do have all of the properties of a reduction that we need, right? And remember what we discussed last time, and again I'm going to emphasize that, is if we have a reduction from problem A to problem B, then we get one important implication, which is if problem A is uncomputable, then problem B is also uncomputable. Right? So if you could build this oracle in the sky, if there's a machine for solving that, then I'm solving halt, which we know is impossible. So what do we conclude from that? We conclude that halt on 0 is uncomputable. Okay. Any questions about this? I say it's a few lines, but there is some meta programming happening here in that we are manipulating source codes of programs. Okay. Go ahead. Yes, yes. Usually, in fact, when we're doing more software writing, it's the other direction that we use, right? But here we're using it kind of the negative direction, right? If you've done CS 180 and you've seen NP completeness and reductions, they're kind of a similar flavor, right? So for example, you might have seen reductions from 3SAT to some other problems and concluded that if one problem is NP complete, then the other problem is NP complete and so on. Okay, so here we are doing reductions at the level of showing uncomputability. There you are doing reductions, I think, they're a little bit more fine-grained. Okay. All right. Let's do more examples so that we kind of understand this concept well. Let me define, give you another example, which is not empty. Okay. So not empty again is asking about programs. Okay. It takes a program as input and checks if there is some input which makes a program output 1 and is 0 otherwise. Okay, very simple task. I give you a program as input and I ask you, okay, is there some input which makes you output 1 or not? Okay. And theorem is not empty is unfortunately also uncomputable. So just as an example, let's say someone, for whatever reason, gave me this program. Okay, so let's say this is my program. If the input is 0, you return 1, otherwise you return 0. Okay. What is not empty of this program? If I call the function not empty on this program, what would the output be? It's just asking, okay, is there some input which makes my program output 1? And the answer is yes. If I give it 0, then I would get 1. Right? And in the same way, if I give it some other program, let's say, let me call it Q, and you say return 2, then not empty of Q would be 0. Okay, here, you can easily imagine that I can at least write something which can look at the source code and tell me whether or not this is true. Right? Okay. But it turns out that in general, not empty is very, very hard problem. It's an uncomputable problem. Okay. And I should say not empty is not just like a theoretically interesting thing. It kind of shows up in many places practically where it is an important problem that we would like to solve, but nevertheless we cannot. Okay. All right. So we are going to do this again by reduction. And so when you're trying to do reduction, the first thing that you need to decide is what is my starting problem? Okay. Which one should I pick among all of the things that I know are uncomputable and reduce that to my problem? Okay. Here, any suggestions for what might be a good candidate? What problem should I start from? Okay, so we're going to use reductions. So I need to pick some problem. At least the target is clear. The target is going to be inputs for not empty. Okay. But what should my starting problem be? Any suggestions? Well, we have 3 uncomputable problems. So which one should we pick from those 3? We know toddler, we know halt on 0. We should pick the simplest one in some sense. And I would say the simplest one is halt on 0. Okay, so I start with some thing like this, and I get here. Okay, so I'm transforming programs to other programs, and my claim is that I want a reduction which preserves, which helps me answer halt on 0. So if I give you any program as input, then what I get is exactly this. Okay? Any suggestions on how I might come up with this reduction? So I'm giving you some program as input, right? I want to check if this program halts on 0 or not. That's my only thing. And I want to transform the source code of this into something else. Any ideas? No? Okay, so let's see. Let me give you a hint. Again, so we are going to come up with a new program. Let me call it N, right? And the property that we want is if my input M halts on 0, then the new program should have at least one input where I get a 1. Okay? Whereas if it doesn't halt on 0, then I should not have any input where it halts on 0, where I get output 1. Okay? So any suggestions on how I might build this new program? It's really just 2 lines. I'll write down one more line for you. It's just return 1. What should the previous line be? Well, we can just do eval of m comma 0. Right? So what is it saying? Okay, I'm going to write down the instruction which says run m on 0. Okay, and then go to 1. That's it. Right? So if my machine m halts on 0, then I would actually terminate here and get to a point where I'm returning 1. Okay? So there are many, many inputs where I would return 1. In particular, there is 1. Right? In fact, on every input, I would return 1. Okay, that's fine, right? So claim is halt on 0 of m equals not empty of m. Okay? And we can check this easily. So if halt on 0 of m equals 1, then what happens? So you're saying if m halts on 0, then I'm going to stop here and enter the second line. So I would get not empty of m equals 1. Right? So on every input, n outputs 1 if m halts on 0. In particular, there's at least one input which makes you output 1, so we are fine. Right? And on the other hand, if halt on 0 is 0, meaning m does not halt when the input is 0, then I would get into trouble. And my new program would always output 0. Okay, does it make sense? So once again, the confusing thing here is that we are manipulating source files. I'm not really executing anything. My reduction is not doing anything. any execution, is taking the source code of M and writing down a different source code, right? And we're pushing all of the hard work to our oracle in the sky, which is supposed to be able to solve not empty. Okay, any questions about this? Yeah? That's okay. For now, I only care if M halts on 0 or not, right? So that was what I was asked to answer. This makes sense? So I just needed to know if M halted on 0 or not. If there is some other input it halts, that's okay. That's a different problem for me. That's a different problem than the one I am set to solve. Okay? Yeah? Mm-hmm. No, because the input to N is Z, which is not even being used. Right? Maybe the other way to think about it is we're using not empty on a very special program, right? In fact, it either is it outputs 1 on everything, or it doesn't output 1 at all. Even this, we are not able to tell apart. Does it make sense?
Because let's say M falls on everything other than 0. Wouldn't the not empty return 1? But in this case, val never finished. Doesn't fall. You get 0.
Well, that's fine, right? Because the inputs for not empty and halt on 0, they're completely different things. I'm just using the oracle calls for not empty to answer for halt on 0. We're not doing the other direction. I think what you're asking for would be to say, okay, can I solve not empty using halt on 0? That's not what we're doing. We're just saying, if you give me a program M, I just want to somehow find out if it halts on 0 or not. Then I'm going to write down this new program and push it off to my oracle in the sky, and it is going to give me an answer, and that answer is going to be correct. This, whatever I'm pushing into the sky, has many additional properties. That's okay. And I don't need to use that. All I'm saying is that as long as you can give me the answer to not empty, I'm solving something that should be impossible to solve. Okay? Yeah? We are trying to solve halt on 0 with the, someone gave us a superpower to solve not empty. It is a superpower because it's impossible, right? And all we are doing is transforming the input. Okay, we're not calling not, or at least we're not building an algorithm to solve not empty. We are pushing it all into the sky and saying, okay, go ahead, solve it for me. And the problem with that is that if you can solve it, you end up doing something impossible, so you should not be able to solve it. Okay, yeah? Say it again. Oh, program for R? Yeah, so basically it would say, that's a good question. So let me maybe tell it once. The program for R would say, take the input source file for M, okay? Take the source code for eval, right? So load up eval with the source code for M followed by 0. And then say return 1. Okay, so we are implicitly using the fact here that this is computable. Right? Meaning I can write down the entire, if I was doing in Python, for example, I would have to write down the entire compiler for Python right there. That's implicit. Like when I say, if you go here, for instance, I'm calling this guy, but if the whatever black box that I'm calling in this guy does not have access to the compiler, you're basically pasting the entire source code for Python 3 there. Does it make sense? It's a huge text file with the entire source code for the compiler, followed by the source code for M, followed by X. That's what you're pushing to the cloud. Okay? And we're kind of using shortcut here and saying I'm writing down eval here, meaning I'm writing down the instructions for eval. I'm not executing, I'm just writing down the instructions for eval.
this right? No.
Eval needs to be computable, but we know it is computable, right? So yeah, you're very right to point out that we are using the fact that eval is computable here strongly. So we are using universality here. Okay. All right. So let me do one more example. Again, depending on your perspective, these are either how many of you remember reductions from CS 180? NP completeness reductions. I see a few people raising their hands. Depending on your perspective, I would say, arguably these reductions are a little bit easier on one axis in that you don't have to respect so much the inherent constraints of the problem. Like in CS18, in this NP completeness reductions, you might have said, okay, reduce 3 SAT to like some clique problem or something, right? Whereas this, in that sense, this is a little bit easier. But on the other axis where it's harder is this conceptual thing where you have to think of manipulating source codes and not inputs. Okay. So once you take that step of just treating programs as inputs, things become a little easier. Okay. All right. So let me do one more example. This one I'll call I'm just making it up on the fly, exactly 1. Right? So exactly 1 is saying, okay, tell me if there is a single input which would make M accept or not. If there's a single input where M accepts, then I would say 1, otherwise I would say 0. So going back, for instance, if I copy these 2 programs, what do I get? So exactly 1 of P would be, does it have this exactly 1 property or no? See a few people nodding their heads. So yes, right? Because there's a single input which would make P output 1, which is 0. Okay. And here, okay, let me change it a little bit and say, what if I say Z equals 0 or Z equals 1, you return 1. Okay. And I see some people shaking their heads, so, and that is correct. Now, the answer would be 0 because there are 2 inputs which would make it output 1. Okay. It's a very dummy example, kind of a useless program to compute, but let's just take it as an example to learn from. Right? Okay. We have a new function, and my claim is, again, this is also uncomputable. So I said, once you know where to look, uncomputability is easy to find. There are lots of things which are basically no computer can solve. So how can I prove this? Any ideas? Any suggestions? Again, we're going to use a reduction, right? So you have to decide what is the starting problem that I'm going to reduce from. So let's pick something that we've done so far. So what would be your choice for the starting problem? Okay, so what do you want to do? We want to prove this by reduction. So we want to pick one problem that we know to be uncomputable, and then go from there to exactly 1. So what should I start from? Any sessions? No, yes. Yeah. I can do it from halt, but it'll take me a little bit longer. Halt on 0. I would say, halt on 0 is the most friendly starting point. But you can also start from not empty, for example. Okay, so when you get home, I would maybe just as practice try to even do it from not empty. So that's how you can get a sense of what's a good problem to start from. Okay. So what are we trying to do here again? Halt on 0. I take a program as input. I have to output another program. But the property I desire of the new program is a little bit different, right? So we kind of start with the same exact setup. We want this equations. So I'm going to be lazy and okay, this is what I want. And I need to change these guys, obviously. Okay, so how can I change the program to be exactly 1 now? Any suggestions? So I would say what we did just now almost does it, except have lots of inputs where I'm outputting 1. Right? So how can I fix that? Yeah? Exactly, right? So, I can basically do the same thing here, add 1 extra condition. I'm even lazy to write down 2 extra lines. So I'll say if z equals 0, then, all right. Okay. So that's it. So I'm kind of putting 1 extra constraint to say the only place where you can ever output 1 is when z equals 0. But that also is conditioned on m halting on 0. Okay, does it make sense? Yeah. So we're not, I'm just writing down the code for n. Right, so I'm not running n. So z is just a placeholder for the input name. Okay, so I'm writing down the instructions for n, the source code for n. And z is just a variable name there. Does it make sense? So so think of n as a program. My reduction is only outputting these instructions. Oops. It takes m and outputs this new program. Whether I call it z or x, it doesn't matter. It's a program, and now I'm pushing it to the cloud and asking exactly one to tell me, is there an input? Is there exactly 1 input which would make my program output 1? Okay, so kind of the tricky thing here is we are never running n. Okay, we are not. We are pushing it to the cloud or a magic Oracle box, whereas we are just writing down the source code for this new program. Okay, and so this I could just call it anything else, it wouldn't matter. Does it make sense? Like it's just an input name in the program.
Is it ever fed like?
By the Oracle, it can, but we are not doing it, right? So think of it as like I'm writing down a Python program, the instructions for the program, right? The input for that is whatever the other person can feed it. And my job is to just write down these instructions for the program. and I'm giving the program to somebody else, they can do whatever they want with it. They can feed a specific Z if they want. I don't care at this point. I'm just writing down the instructions and passing the buck to this magic oracle in the sky. Okay.
Professor?
Right? So we can check again, what's happening here. This case analysis is almost exactly the same. So what do you want to do? We have to check the utility. So we say, I want halt on 0 of m to equal exactly 1 of n. Okay. And the reason this is true is okay. And on the other hand, if my m never halts on 0, then I have no input that would make it output 1. Right? So once you come up with kind of the reduction, arguing its correctness is just like checking the two cases, more or less. Okay. Any other questions about this? As I said, it's a little bit confusing again because we're really operating in a space that we don't usually operate on. Right? We are operating in the space of source code. So we're changing one source code to another source code without really executing anything. We're pushing all of that to these magical boxes that we want to show don't exist. Yeah? Yes, it is arbitrary. You can put any number there, it would just be equally valid. For the reduction, they would give you different programs, but for the reduction, it would be equally valid. Yeah?
So the reason why we put that is there is so that output.
Exactly, yeah. Right? If I told you exactly 2, then maybe you would put 0 or 1 or something like that, right? Okay. All right. So let's take a 5-minute break. And when we come back, we'll see that to our massive misfortune, uncomputability is not just here. It's really pervades most of software engineering. Okay. And maybe that's what makes it more interesting for us anyway. All right, let's get started again. And so, as I said, if you know where to look, uncomputability, unfortunately, is everywhere. And one of the most important areas where it is everywhere is software verification. Okay. So have you taken any classes or any classes where software verification kind of showed up as a topic or problem that you would like to address? No, yes. Okay. Software verification is basically this field where you have a program and you have a specification and you want to know if the program actually has this property or not. Right? So, I gave a programming assignment and you gave me a program and I want to check if this program is solving the problem in the assignment or not. Okay? Usually the way you do it is to run some test cases and so on, but there will be ways to cheat if you're only running a few test cases, right? But fundamentally, you can ask, can I answer the following question? Okay, I have program A, and I have program, maybe let me use M and N. Okay, these are two different things, and you want to check if they are equivalent or not. Are they doing the same exact thing or not? Right? So for example, we can take this dummy program. If n is less than 0, then return 0, else return 2 times n. Okay. And then I can take another program, which is, let's say, less than or equal to. If n is less than or equal to 0, you return 0. Okay. Otherwise, I'm going to say really silly way to compute the double of a number. I'm just adding 2 to itself n times. Okay. Now, these two programs are equivalent to each other, meaning on every input, they have the same exact behavior, right? And you can imagine how useful it would be if you can do this in an automated way, right? So can I check if these are computing the same function? Okay. And if you can do this, this would really, really be helpful in the field of software verification. And testing, basically you have some implementation goal in mind, right? And then you might have heard of this concept called unit tests and so on, but basically there are ways to get around or ways to attempt at solving this problem, right? I have two programs. I want to check if they're exactly the same, or I have a program and I want to check if its behavior matches what something else I have in mind. Okay, it would definitely make grading programming assignments much easier. Okay, where else might verification be useful? Any other guesses? So one of the most important places where it shows up is security. When you're trying to detect attacks, it would be very helpful if you could verify what the software is supposedly doing. Okay, and even in hardware verification, for example, also you can set it up this way. Okay, so it's really okay. If I can verify two programs are equivalent or not, I would solve many, many important practical things. Okay, but it turns out that all of these are uncomputable. Software verification is fundamentally not possible. Okay, so that's why we have all kinds of heuristics and ways to get around this uncomputability. Okay, to formalize this, actually, let me introduce a very nice conceptual idea, and this goes back a long way, to the 1950s or something, but keeps showing up again and again. And this is the notion of a semantic property. Okay. And you should think of semantic properties we are talking once again at a meta-programming level about properties of programs, right? Not the input output. I'm not asking you to compute the input or compute the output on some specific input, but I give you the source code and I'm asking you some property of this source code. Is this source code equivalent to the function that I'm computing? Does this source code have some malicious property? Is it going to cause me to go into an infinite loop, and so on and so forth? Okay. So I have a function which is just 0, 1, and think of this f as taking inputs of programs as input. Okay. And we say f is a semantic property if f only depends on the input output behavior of M. Okay. So in some sense, I give you a source code, I ask you to verify some whether or not it has some property or not. Okay. As long as this property depends only on the input output behavior of the source code. Like if I change a variable name, it shouldn't change whether or not it has the property. If I change how I write down the code, it shouldn't change whether or not this program has the property. Okay. So more formally, you would say something like this. F is semantic if for any two equivalent programs, m, n prime, right? So equivalent means that for every x, m of x equals m prime of x. Okay. Does this make sense? So just the definition. So it's a semantic property if it doesn't depend on the actual syntax of the code. It depends on what it is actually computing. It depends on the input-output behavior. Okay. So for instance, these two programs are equivalent to each other, right? Because on every input, both of them give the same answer. But syntactically, they are very, very different. Right? Does it make sense? So these two are equivalent programs. Okay. And a property or function on programs is semantic if on any two things which have the same input-output behavior, your answer is the same. Like for example, I ask, okay, does it go into an infinite loop? The answer would be the same for both. Okay. Any questions about the definition? No? Yes? Okay. So, in some sense, many of the things that we looked at so far, like not empty, exactly one, halt on 0, these are all semantic properties. They really depend on the input-output behavior of the program as opposed to how you're actually implementing it. Right? If I change the variable names, whether it's going to halt on 0 is not going to change. Right? You gave me a program, I rewrite by ordering some things, introducing some dummy code. It's not going to change the input-output behavior. Okay? And there's this really beautiful, but also very pessimistic, or kind of, let's say sad theorem called Rice's theorem, which says that every non-trivial semantic property is uncomputable. Okay. So what does non-trivial mean? Non-trivial just means that anything which is not the constant zero function or the constant one function. Oops. Yeah, okay. Okay. So any semantic property which is not always outputting 0 or not always outputting 1, meaning, okay, is somewhat of a meaningful function. There are two inputs where it outputs 0 on one and 1 on the other. Any such thing is uncomputable. Okay, does it make sense? Does the statement make sense? Okay. So let's see, what it would imply. So for example, halt on 0 is a semantic property. Right? So you can think of it as, really it takes programs as input. Okay? Right? So halt on 0 takes programs as input, but what it outputs really doesn't depend on just the syntax. It depends on what it is actually computing. Right? If I change the variable names, the output of halt on the answer of halt on 0 is not going to change. Right? Does that make sense? Yeah? Halt on 0 is a function, right? But the function takes two programs as input. And it's saying as long as the two programs are equivalent, the value of the function should be the same. Okay, if they're equivalent, then the value of the function would be the same. Yeah? Well, then we have to do something else. But right now, at least, we're only studying semantic properties. And the reason it's a very nice class is because many times what we care about in software engineering are semantic properties. Okay? So that's the reason why this was studied extensively. Right? So for example, what is this saying? So why is it semantic? Well, if we have two equivalent machines, m comma m prime, then halt on 0 would by definition equal halt on 0 of m prime. Right? Because m and m prime, they have the same behavior when the input is 0. If one halts, the other should also halt. If one doesn't halt, the other should also not halt. Okay? And in the same way, you can show that not empty is a semantic property. A semantic property is just like, is a function as well. But since we are talking about functions which view their inputs as programs, we're just making the distinction more explicit by calling it a property. Right? So not empty is also a semantic property, because if I have two machines, M is equivalent to M prime, then not empty of M is the same as not empty of M prime. Okay. So it doesn't depend just on the syntax. It actually depends on the semantic property, the input-output behavior of the program. Okay. And similarly, we also get that exactly 1 is also a semantic property. Okay, so we individually showed that Halton 0 is uncomputable, not empty is uncomputable, exactly 1 is uncomputable, right? But really they're all uncomputable because they're all semantic properties. And they're non-trivial, you have to verify that, but that's clearly true, right? These are definitely not always outputting 0 or 1. Okay, so it's a very weak constraint. Non-triviality is very weak constraint. You're just saying, okay, I'm not always 0. The trivial 0 function or the trivial 1 function, if I exclude these two, everything else is uncomputable. No ifs and buts. Except for these two things, every semantic property is uncomputable. Okay. So we could have gotten all of these things as a corollary of Rice's theorem, but the way you prove Rice's theorem is to use one of these as uncomputable. So that's okay. Any questions about the statement of the theorem? Yes, no? Okay, all right. So, like for example, let's say, how does this connect to software verification, for instance? Maybe let me use power 2 as an example. Okay, so answer equals 1. Okay, so let's say if n is less than or equal to 0, you return 0. Okay, otherwise you say answer equals 1 for I in range of n. Here's a dummy program. We just computes the power of a number, the 2 to the n, where n is the input. Okay. Now imagine, I give a programming assignment where I say, write me a Python program for computing power 2. Maybe 90% of you would do this, but I'm sure 10% will find many ingenious ways to write the same program. Okay, so there are very, very different ways. Maybe I'll use repeated powering, repeated squaring to do it faster. Who knows? I can give you very, very different things. Okay, and I can define a new function now. Again, it's a function which views programs, which views its inputs as programs. E is power 2. Okay, so E's power 2 is just like a checker, like a grader, which takes your submission and checks if it's computing the exact same function as I wanted you to compute. Right? So I ask you to implement power 2, you gave me some submission, and is power 2 is my grader, which just checks, okay, is it computing the exact same thing or not? All right? And my claim is that this is uncomputable. Is power 2 as a function is uncomputable. Seemingly very simple, but it is uncomputable. Why? Yeah? It's a semantic property. We don't even have to think now. It is a semantic property, and it's non-trivial semantic property, right? You have to check non-triviality, but usually checking that is like, okay, just 2 lines that you have to write down, but it is semantic, non-trivial, hence it is uncomputable. Okay, but this is like these are the kind of problems that you would need to solve in software verification, right? Claim is power 2 is a semantic property. And hence is uncomputable. Okay, and why is it semantic? It's kind of implicit in the definition, right? So to show a semantic property, we need to show that if I take any 2 equivalent machines, then the output of whatever function you're the value of whatever function you're investigating is the same, right? But that would be true because is power 2 checks if m is equivalent to this program. Is power 2 of m prime would check if your other submission is correct, right? But both of them are kind of the same program, right? That's what equivalence means. Okay. Any questions about this? You have to check non-triviality, but that's easy to do, as I said. Right? In the same way, you can define, okay, is majority. Suppose I want a program which computes whether or not the input has more ones than zeros, and ask you to write it up. You give me 200 submissions. I cannot build a grader which will just look at your submission as code and tell me if it is correct or not. Okay, so that's kind of the sad part, that every one of these semantic properties, except for the 2 trivial ones, is uncomputable. And in programming languages, in software engineering, and so on, we often study semantic things. We are not exactly interested in what variable names you use. Did you use extra spacing somewhere? Did you use some extra dummy variable? Did you write it with a for loop versus a while loop? We're not interested in that. We are really interested in detecting input-output anomalies or things like that, right? But this is saying all of those are uncomputable. Nevertheless, we basically that allows, in some sense, we try to get around this by developing heuristics for this. Okay. Any questions? Yes, no? All right. So, Rice's theorem, as far-reaching as it is, it's not too far-fetched from, the proof of Rice's theorem is not too far from what we already did, but I'm not going to cover it. Okay, but just understand the theorem. First, there's this very nice definition of semantic property, right? 2 programs, if they're equivalent, my function value should be the same. Meaning, I'm not interested in your syntax, how you wrote the code. I'm only interested in what you are actually computing, right? And unfortunately, every one of the semantic properties is uncomputable. Okay. So in summary, one way to summarize this is basically any meta-programming tasks is uncomputable. By meta-programming, I mean where you ask questions about programs. So reasoning about programs is perhaps one of the hardest things you can ask a computer to do. Okay? You cannot write a program which can effectively reason about other programs. Okay? It cannot answer questions about other programs. All of those are, any useful one is going to be uncomputable. Okay? But this is one. The second thing is that uncomputability is not just limited to meta-programming things. There are problems that arise in many, many different fields which also turn out to be uncomputable. You can design questions about puzzle pieces, whether or not they fit in some ways. Those turn out to be uncomputable, for example. Solving integer equations, for example, which has nothing to do with programs, right? You might think, okay, maybe uncomputability is only coming up because we're asking ourselves to reason about programs. That's not true. It can show up in places where there are no programs involved. If I give you a bunch of integer equations and ask you to solve it, that turns out to be uncomputable. Okay, this is a famous result in logic and mathematics. This is called Hilbert's 10th problem and so on. Okay. So uncomputability can show up. There are various questions in physics which turn out to be uncomputable. We can design various games where checking if one player has a winning strategy or the other player has a winning strategy also turns out to be uncomputable, and so on. Okay. So in some sense, Turing machines are very powerful. They are as powerful as there can be. But with this power came this severe limitation that we cannot reason about them effectively. Okay. So what we'll do in the next class and kind of maybe next 2 lectures is to bring down the power of Turing machines a little bit so that we can still do something useful, but at the same time be able to reason about the model. Okay. And I'll give you an example of why this can be very useful practically. And one place where it keeps showing up is in the space of cryptocurrencies. Have you heard of smart contracts? Yes, no? Okay, so there, you really want to limit the power you allow so that you can verify certain things. Okay, and if you cannot verify, then you run into big, big trouble. Okay, we'll talk about that in the next lecture. Yeah? Yeah, this is the last lecture for exam 2. So everything up to Rice's theorem, the statement of Rice's theorem, semantic properties, and so on is in the exam.